College Algebra, Chapter 6, Section 3, Solution of Linear Systems by Row Transformations. Solving linear systems of equations can be streamlined by using matrices, and the singular of that would be a matrix. Now, when we talk about a system of equations, what we're talking about are multiple equations that involve multiple variables. And the general rule tends to be that you need as many equations as you have variables. So if you have 2 variables you're solving for, you need at minimum 2 equations. If you have 3 variables, you need 3. And these equations make up a system of equations. So consider the system of 3 equations with 3 variables here. We have a sub 1x plus b sub 1y plus c sub 1z equals d sub 1. A, b, c, and d are constants. They're real numbers. X, y, and z are our variables. Now we can write these in a matrix, and a matrix is just an array of numbers. You have a certain number of rows and a certain number of columns, and it's a way of organizing them. And how we organize them is we write just the coefficients down. You'll notice that the first row is all a's, and those are all coefficients of the x terms of the 3 equations. The second column is all b's, and the b's are the coefficients on the y's. Then you have the z coefficients, and finally the answers. The columns go vertically up and down. The rows go horizontally across. You'll notice each row represents a particular equation. The array of numbers enclosed by brackets, like we just saw, is called a matrix. Each number is called an element or an entry. The contents in the last column of the matrix can be set apart from the coefficients with a vertical line, creating what is known as an augmented matrix, which looks like this. So what that does is it tells us that the first set of 9 there, those are all coefficients. The last ones are constants. They are the solutions to the equations. Now, here's an example. You have a set of 3 equations, and you have the augmented matrix formed by them. Take a moment and look over this, and make sure you have it. If you need to, pause the recording for a minute so you can study it, because we're going to be changing the equations into these augmented matrices. You can put matrices in your calculator. What you're going to do is you're going to press second and then the x to the minus 1 button, and that will bring up the matrix menu. Then what you need to do is don't hit enter, go over to edit and click on edit. And the first thing it'll do is it'll give you an opportunity to put in how many rows and how many columns. Rows comes first, columns second. So you put in the number of rows, in this case 3, hit enter, and then 4 and hit enter. And then you're ready to start putting in the numbers. And just hit enter every time you put in a number. You'll notice at the bottom of the screen it shows you what row and column you are currently putting a number in. And when you're done, you can do second mode and quit from that. And then what you can do is you can go to matrix and then select A under names and hit enter, and it will actually bring the matrix onto your home screen, which is what you're seeing here. Okay, the row of an augmented matrix can be treated just like the equations in the system of equations. Now, if you remember, you probably have done these before. More than likely, you did them a little bit in Algebra 1. Sometimes what you have to do when you're trying to solve a system of equations is you might add 2 together because you want one of the variables to drop out, or you might multiply one of the equations by a number and then add it to another one in order to get a variable to drop out. And you can actually do that with the different rows in the augmented matrix. Here are some rules for dealing with augmented matrices. Any 2 rows can be interchanged, so you can swap out 2 rows. The elements of any row can be multiplied by a non-zero real number. So you cannot multiply everything through by 0, but you can multiply it by anything else, fraction or whole number or integer. Any row may be changed by adding to its elements a multiple of the corresponding elements of another row. In other words, you can replace a row by multiplying another row by a number and then adding that row to it. And we're going to be working with each of these. I'm also going to give you a program called Row Ops that's going to help make things a little easier with this, with the math of it. You still need to understand the principle of how to do the changes. So we're going to use matrix row transformations to change this matrix into each of these. Now what I want you to do is I want you to write next to the row what happened to change it. Okay, what happened? Did did they swap? What happened? Did they multiply by something? What made the change from the original to the one you're seeing? Pause the recording, give this a try, and resume to check your answer. Okay, the first matrix, all they did was they swapped two rows. Row 3 is unchanged, row 2 and row 1 were swapped. In the second one, the only thing that changed was they multiplied the top row by -2. So everything there has been multiplied by -2. And then in C, they multiplied the first row by -1 and added it to the third row. So its corresponding element, in other words, its matching position. And what that did was it changed row 3. So notice by row 3 it says negative row 1 plus row 3. And you see how those have been changed. We use row transformations to turn our augmented matrix into a matrix that is in echelon or triangular form. Echelon form of a matrix has ones down the diagonal from upper left to lower right. That's called the main diagonal, you see here. And you have zeros below each one. So above the ones, you've got numbers. Below and to the left, they're all zeros. Once a system's in echelon form, you can use back substitution to find the solution set. In other words, we will take this and change it back into 3 equations, and that's going to let us solve for what each variable is going to be. The row echelon method uses matrices to solve a system of linear equations. You start by getting 1 as the first entry in the first column, so you do what you need to do to make that happen, and then you transform all the entries below that to 0. To get a 1 in the first column, usually you're going to usually you're going to multiply the first row by something to make that happen. And then we're going to use our row operations to get the zeros below that. And we continue doing this until we achieve row echelon. So once we have the first column as 1, 0, 0, then what we do is we go to column 2 and we make the second row, second column a 1, and then below that has to be a 0, and then you keep going across the matrix. You don't mess with the numbers on the other side of the vertical line. So we're going to solve a really simple system here. We just have 2 variables, change it to a matrix, and why don't you give this a try? Pause the recording, give it a try, and then resume to check your answer. Okay, there's our initial matrix. Now remember, we want to get a 1 in the upper left corner. So what we do is we multiply 1/5 by row 1. And here you've accomplished that. So we have 1, 2/5, and 1/5. Don't let the fraction freak you out. Now our next job is to make that 2 below the 1 a 0. So what we're going to do is we're going to multiply row 1 by -2 and then add it. So -2 times 1 is 1, plus 2 is 0. -2 times 2/5, -4/5, minus 1 is -9/5. -2 times 1/5 is 2/5, plus 4 is 18/5. Now we're going to make the -9/5 into a 1. And we're going to do that by multiplying by the reciprocal, -5/9. And now we're really done with changing our matrix around because there's nowhere else to go. There's nothing under that 1. So now we rewrite our equations. We have x plus 2/5 y equals 1/5, and we have y equals -2. Well, now we know what y is. So substitute -2 in for y and solve for x. And we get 1, -2. Now let's try this one. We have 3 variables this time and 3 equations. Pause the recording, give it a try, and resume to check your answer. Okay, here is our matrix. And the good news is that the upper left number is already a 1. So we don't need to change our first row, but we do need to change second and third to make each of those equal to 1. In order to do that, we are going to multiply the first row by -3 and add it to the second. And we're going to multiply the first row by -1 and add it to the third. And that results in what you see here. Okay, the next thing we're going to do is we're going to need to change the 6 in the second row, second column into a 1. So we'll do that by multiplying by 1/6, as you see here. And then we're going to need to make the 4 below it a 0. So we're going to multiply row 2 by -4 and add it to row 3. And the last thing we have left to do now is to change the 23/3 into 1. So we'll multiply, and there we have it. Now we've got our system. We have 3 equations, but these will be easy to solve because we know now that z is -1. And we can use that in the middle equation to solve for y, and then use both of those answers to solve for x. And we get 1, 2, and -1. Now, row echelon is great. It's got 1s along the diagonal and 0s below. But there's another method called reduced row echelon. This has 1s along the main diagonal and 0s both below and above. And the beauty of it is that when you get it to look that way, the numbers on the right side of the vertical line are the solutions to the equations. You're done solving. This form is achieved in a similar manner to row echelon. So you have to do a few more operations to get it to happen, but you can make it happen. Now this is an example of what we mean by reduced row echelon. Here you see we have our 3 systems and we put them into the form of a matrix. Now this doesn't go through the process right here, but when you transform the matrix, you want to transform it till it looks like the matrix you see on the bottom there. And that's what is called reduced row echelon form. And when you look at that, the top row you have 1 in the place of the x, and the answer for x is 3. You have 1 in the column for y, and then go all the way across and you get 2, and then z is 1. So the advantage to this is that once you've gotten it in this form, you don't have any additional solving to do. You know what x, y, and z are. One is whenever you have the row of an augmented matrix in the form of where everything is 0 except for the number on the other side of the vertical line, and A is not 0, that has to be something else, the system is inconsistent and there will be no solution. Because basically what you're saying in this row is that 0 equals a number other than 0, which is not true. If you have a row that's all 0, including the number after the vertical line, the equations are dependent. In other words, you cannot get one singular answer for each variable. There are many answers that will work. The system is inconsistent. Why don't you pause the recording, give this a try, and then resume to check your answer. Okay, so here's our matrix. And here what we did was we multiplied -2 times row 1 plus row 3. So row 1, column 1 already had a 1. So we need to make the numbers under that 0. And just to shorten things, because we're trying to prove a point here, they went ahead and jumped straight to the last row and tried to change that first number to 0. And when we did that, the whole row, except for the number on the right side of the vertical line, is 0. So you have that 0 equals 1, which is not true, which means this is inconsistent and there is no solution. By the way, if you remember, the 0 with the slash through it is the symbol for the empty set, which is another way of saying there's no solution. There are no numbers in the set of answers for this, of solutions. Where the equations are dependent. So it says, show the system has dependent equations, express the general solution using arbitrary variable. Now, that second part may not make much sense, so don't worry about that. But pause the recording and try your matrix skills out and see if you can get it to where it shows that it's dependent, which means one entire row, including the number on the right of the vertical line, is 0. Pause the recording, give it a try, and resume to check your answer. Okay, so our augmented matrix is this right here. And we're going to go to the next slide for the the first thing they did was they multiplied -2 times row 1 and added row 3. Now, normally we don't jump straight to here, and you may have, changed the first column, first row, first column to 1 as normally we would do, and that's fine. But eventually in your solving, you're going to get that row 3 is all 0, which means we have a system of dependent equations. So the first two rows represent the system, which means we have 2x minus 5y plus 3z equals 1, and x plus 4y minus 2z equals 8. Take those two equations, and we're going to create an augmented matrix with those. And since the final equation doesn't matter, it's not helping us at all, we got rid of that. What they do is they say, all right, first thing we're going to do, we're going to try to get this in, as close to echelon form as we can. Now, we're not going to be able to get it completely there because you really need to have 3 variables, 3 equations. We only have 2 equations. But we're going to go ahead and make our row 1, column 1 a 1. And we're going to try to do the same with row 2, column 1. So we're going to swap rows 1 and 2, which is just the easiest way to get a 1 there. You could multiply row 1 by 1/2, but it's just easier to flip them around. And then we make the 2 underneath of it 0 by multiplying row 1 by -2 and adding row 2. And that's what you see here in this final matrix on this slide. There's our second now. Okay, the top matrix you see here is just a carryover from the previous slide. So this is what the last matrix on the previous slide was, just so you don't need to switch back and forth in case you've forgotten. So we're starting with this. We want to change the -13 in row 2, column 2 to a 1. So we're going to multiply the second row by -1/13, and it gives us some really weird numbers, but that's okay. So we have a 1, a -7/13, and a 15/13. So now we have 2 equations. We have x plus 4y minus 2z equals 8, and y minus 7/13z equals 15/13. Now what we're going to do is we're going to solve for y, and it'll be in terms of z. So we get that y is 15/13 plus 7/13 times z. What we're trying to do is express our 3 solutions using z as the variable. And so we solve for y, and then we go back to our first equation, and in place of y, we put 15/13 plus 7/13z, and then we solve for x, and we get x is 44/13 minus 2/13 times z. So our 3 variables, it all kind of depend on z. Whatever z is will determine x and y, and that's why we write them like this. Practice. So pause the recording, give these a try, resume to check your answers, and proceed like this until the end of the recording.